anybody. It's a whole sphere fail.
I know right now.
You guys on the game. You totally.
He was a juice.
It was crazy.
That's why I just.
I don't wake up and be like, oh, I did not want to, that's a joking.
What? Someone said they did the right thing. Not me, maybe it's one Thursday, but not me on Thursday.
Okay,
Look at the dog.
today, we're going to kind of, continue with the topics that we've covered from before. So we talked about, being able to find algebraic limits. We're able to determine, what it looks like when a limit exists, what it looks like when a limit doesn't exist. And we're going to extend that to this topic called continuity. And so we're going to be on page 11 in your packet. Now we're going to be seeing some notations that we're not familiar with, but I want to kind of give you a big picture as to what we're basically trying to achieve using things you've seen before. Okay, so you guys don't have to write this down, but before we get to the notes, I just want to just start off with this diagram that I think is familiar to you. So if I ask you for two things here. Okay, if I ask you to graph those two pieces of information onto the graph, let's just see what that looks like. Okay, so we know what a point is. We just plot that order pair. Order pair at 3, 4. The second statement, remember if I asked you to create a limit, I always say start with a hole and then extend in both directions, right? Because we want the graph to approach the y value from both sides, but we start off with a hole there because we don't know if there's anything that should be there or not. Okay, so what if I inserted this piece of information onto a graph? What do you notice? Yeah, that hole is getting what? Getting filled in, right? It's getting filled in. So what's happening through that point? Is there a break through that point? There isn't, right? So this, we can say that the function is continuous at x equals 3. Right? That makes sense, right? You guys have seen this before. You've seen situations where the hole gets filled in and all of a sudden the graph becomes continuous, right? There's no breaks, there's no asymptotes, there's no holes. So this is basically what we're trying to achieve today. We're going to talk about this topic. There's notations that's going to make this feel more complicated than it really is, but really this is the big picture here, right? If I have a limit that exists, and if the order pair is filling in that hole, then I have a continuous function. So we're just basically building on this topic, and you see the big picture. We're just going to fill in the details and talk about the notations that's involved with this topic on continuity. Okay, so the first definition is one-sided limits. Okay, so one-sided limit describes the function's behavior from just the left side or just the right side of the next value. Okay, so we know what one-sided limits are. It's just that we've been using it from a graphical perspective. So I want to make that connection with what you've seen and that you know, but want to give it a more concrete name for it. So let me start off with this piecewise function. This is we're showing two graphs. There's a parabola but the parabola is only going to be showing to the right of one. So you see that there's a parabola here, but it's getting cut off because it's only being defined to the right of one. So this is what the parabola portion of the graph will look like. Next up is x plus 3. X plus 3 is a linear graph. You see that there's x plus 3, y-intercept of 3, slope of 1. But a line usually extends in both directions towards infinity, but it's getting cut off at 1 because it's only going to show to the left of 1. So that's why looks like a ray here where the graph is getting cut off, right? The line is getting cut off, the parabola is getting cut off, but we can call this a function because these two graphs are not overlapping each other, right? They're not going to conflict because they're each kind of taking its own space and own region. All right, so let's say you're given just the function here, the graph here. If I asked you to find the limit graphically from before, what you would do is you would plot points on either side, right? In order for a limit to exist, we have to have an agreement from both sides. And then from those points, we draw arrows towards our destination, towards 1. And what can we conclude just based off of what we know in the past? Limit does not exist. Okay, so limit does not exist. Now, we didn't really talk about why, like what each of those arrows are pointing towards and using that to justify our statement. We just knew that the arrows did not head to the same destination, so we just stopped there and say the limit doesn't exist. But now we're going to kind of give a little bit more detail as to how each of these arrows are headed towards, right? Which direction are they both headed towards? And using the concrete results to justify why the limit doesn't exist. So the first is this notation of a one-sided limit. This is a left-handed limit. It's not a true limit. It's just basically telling us where the arrow is headed from the left side of our target. So whenever you see this notation here, limit as x approaches 1, you see that negative notation there. That just means that I'm approaching my target from the left side of my target. So it's basically what this arrow is doing, right? We haven't learned this notation, but we know, we recognize this arrow, right? We recognize starting with 2 points and drawing our arrows, one towards the left and one towards the right. So this is where we start at a point to the left of our target and we move to the right. Okay, we're headed towards 1 from the left side of 1. So what would you say the left-handed limit is for this function? 4, okay, because we see that the y value is headed towards 4. What about the right-handed limit from the right side of 1? We see the arrows is headed towards a y value of 1. Okay. Okay, so in other words, the limit, the one-sided limit, as we approach from just the left side of 1 is equal to 4. And the limit, if we're approaching from the right side of 1, is a y value of 1. We can obviously tell that these are not in agreement, so therefore the limit does not exist. So we can add to the statement and say that since my one-sided limit are not in agreement, so we're going to practice writing this out here. So since the limit as x approaches 1 from the right side of 1 of f of x does not equal to the limit as x approaches 1 from the right side of 1, the full limit does not exist. Now I'm gonna walk around eventually as we get into this, and I want to kind of help fix some of our potential notations that we may be leaving out. And the reason why it's easy to leave this part out is because this is different than the way that we say it, right? We say the limit as x approaches 1 from left side of 1 is equal to 3 or 4 or whatever. But we never mentioned this f of x, but we need to include this f of x as part of our notation. So maybe the way that you say limit is this: the limit as x approaches 1 does not exist. But this would not be proper notation. We have to be able to indicate what we're talking about, right? Limit as x approaches 1 of what? We got to name that function. Either we have the full expression or we name it f of x. So it's easy to leave this out. So I want to eventually, once we get to continuity conditions, I'm going to be coming around and checking that you're actually putting something there and not leaving it as just a blank space. So we don't want it, we want it this way, we don't want it this way here. This is kind of an incomplete statement, so we don't want to write it this way. Even though this is the way that we say it, that's not the way that we write it. Okay, so now let's look at it from the perspective of if we only had the piecewise function in front of us without the graph, can we still make the same conclusion that the one side limit is 4 and the one side limit is 1? So let's imagine we don't have the graph in front of us and we're trying to arrive at the same conclusion. So the way that you would do it is limit as x approaches 1 from the left side of 1. That means we want to start at a value less than 1. So which of these piecewise function has values less than 1? First or second? Second, because we see x is less than 1. Okay, so that's telling us that, okay, this is referring to this function. So we insert 1 into the second function. So if I insert 1 in for x, 1 plus 3 equals 4. Okay. So same conclusion that we were able to reach if we had the graph in front of us. Okay. Likewise, if I'm approaching 1 from the right side of 1, that means I have to start with values greater than 1. So which piecewise function has values greater than 1? First one. So I'm going to be inserting 1 into the function. 1 squared is 1. So that's why it's equal to 1. So the plus and minus is basically going to help us narrow down which function to use. And then once we get past that point, then we just insert the number directly in for that variable. All right, so let's look at this concept of continuity. So continuity, can we walk along the graph without any interruptions? Okay. Can we draw the graph without ever lifting our pen or pencil? If so, then our path or graph is continuous at that point. There are no interruptions. If we can visually see ourselves drawing the graph through that point without ever having to lift up the pencil to reach another part of the graph, we call that graph continuous. Okay, so no breaks, no holes, no asymptotes. Okay. Now, if a function is continuous, it's easy to spot, it's easy to see, but we need to be able to justify whether a function is continuous or not using these limit notations. This condition is important. We're going to practice this, and we're really going to practice trying to use the notation exactly as it is. Okay? We don't want to veer from the notation there, so we're just going to practice the rest of class writing it out exactly as we see it. Okay, so in order for a function to be continuous at a specific point, the following 3 conditions have to be met. The first is the point has to be defined. So as I go through these conditions, we're just going to create an example, kind of spelling it out. So let's say I have some x value I'm going to call c. F of c is defined. Let's see what that looks like. So I'm just going to pick a random point. This fulfills the first condition because I've created a point somewhere along C. Second, I'm going to create a situation where the limit exists. So maybe I'll start off with a hole, and I'm going to extend the graph in both directions. So here, We can say the limit definitely exists because if I pick points on either side, if I head towards C, the arrows are obviously moving in the same direction. They're headed towards the same y value, and these arrows can be demonstrated by these notations. So limit as x approaches C from the left side of C, that's what this arrow is doing. Limit as x approaches C from the right side of C, that's what this arrow is doing, and they're obviously pointing to the same y value.
Would it be okay if the limit was in the same spot as?
Right, so let's get to that, okay. So far, the way that I drew this, first condition passes, second condition passes. Now let's look at the third condition. Third condition says, look at what we gathered from the second condition and look at what we gathered from the first condition. And we ask ourselves simply, are they in agreement? So based off of what I drew here, is the limit living in the same location as the order pair? No. So here, for this particular instance, this function would not be continuous at x equals c because it did not pass through all three conditions. Okay, so here, the way that I drew this graph, I would say function is not continuous. Okay, so good with that. Okay, so going back to what Morgan was referring to, what if I plotted a point and then I created a limit and then I had that limit be the same location as the order pair, then this graph would pass the first condition, pass the second condition because the graph is obviously headed towards the same y value. And would it pass the third condition as well? Yes, right, because the order pair is at some y value, the limit is at the same y value, they are completely in agreement. We know that if all three conditions pass, there's no choice but for this function to be continuous through that point. So we know what it takes for a function to be continuous. It needs to meet all three requirements. And then we also know when the function is not continuous, if it fails any of the three conditions, right? We would know that it can't be continuous if one of those conditions isn't true. Now, having said that, we have different types of discontinuity. Okay, based off of which one fails, we can conclude what type of discontinuity we're dealing with. Okay, so let's talk about one type of discontinuity. One is called a removable discontinuity. So this is basically a hole in the graph. And a hole in the graph basically is one where it's not continuous, but it is what we call a removable discontinuity, which means that it's only one point away from being continuous. Okay, either a point that needs to be redefined or a point that needs to be defined, but we can simply make one slight change and the function should all of a sudden become continuous. So let's go through each of the conditions and kind of see what that looks like. Okay. So for this instance, does the point exist? Okay, so I say that f of c is undefined. Second condition, does the limit exist? Yes, right. I pick 2 points on either side. I may not know what that y value is, but I do know that if I draw arrows, my arrows are headed to the same y value. So here I say the limit as x approaches c, again, that's something that we have to kind of get used to. We got to put an f of x there. We can't just say the limit exists. Practice representing there has to be something that the limit is referring to. It has to be talking about a function. So then the third condition is what? What's the third condition? Okay. We look at what we gathered. We look back and we say to ourselves, okay, are those two results the same? They're not. Okay, so we say the limit as x approaches c of f of x does not equal to f of c. We're going to write it out exactly as we see it. We may change that c value later on when we know what that exact value is. So this is what removable discontinuity looks like. It's going to pass the first, it's going to pass the second condition, but it's going to end up failing third condition.
Didn't it fail the first one too?
It does. Good question. It's a good observation. The first condition fails. If the first condition fails, you know that the function is not continuous, but we don't know which category we're dealing with until we get to the second one at least. Okay. So when we're dealing with removable discontinuity, we gather the first condition's information, but we have to keep going because we can't categorize between this and this other one that we're going to talk about on the next page until we reach that second condition. So that's the definition here. Removable discontinuity will pass the second condition, but fail the third one. We're still going to do the first condition. We're still going to gather information from the first condition, but we have to look at the second one at least before we can make any conclusion. All right, page 12. So we have removable discontinuity, and we also have something called non-removable discontinuity. So this is, we also call this a step discontinuity or jump discontinuity. This is one where the graph jumps from one connected piece of graph to another. And non-removable discontinuity is going to end up failing the second condition. Second condition is talking about limit. So if I pick points on either side of one, right, are my arrows going to move to the same y value? They're not, right? So let's interpret those arrows that we drew with the more concrete algebraic expression that we're learning right now. So limit as x approaches -1 from the left side of -1. That's basically what this arrow is referring to. What's that one-sided limit? 3, okay. The limit as x approaches -1 from the right side of -1. That's basically following the path of this arrow. Where is that headed? So the one-side limit, one side is going to 3, one side is going to 1. We can say that the limit, what? The full limit does not exist. So if the second condition fails, we can stop and we can say, okay, we're dealing with a non-removable discontinuity. And this is one where if I want to make this function continuous, I can't just replace one point and make it continuous. It's more than that, right? There's more adjustment that needs to be made to get it all the way to continuous. I may have to define a whole second branch to make it continuous. But removable discontinuity is where I can just make one little change and all of a sudden the graph should be continuous. So let me highlight each of the conditions and what it entails. The first condition is, does the point exist? So if the first condition fails, we know the function is not continuous, but we don't know which category. Okay, so we're going to have to keep going. So if I want to categorize between removable and non-removable, I need to gather the information from one and just keep going. So now, second condition. Second condition asks if the limit exists. So if the second condition fails, we know the limit doesn't exist, and we know which category we're dealing with, which is non-removable, and then we can stop. Okay. We're not going to move on to the third condition unless the second condition passes. Now, let's say the second condition passes. That means the limit exists. So we're still going to keep going because we don't know which whether the function will be continuous or whether there'll be a hole. So we're going to continue to the third condition. We only test the third condition if the second condition passes. Okay. Now, third condition. If the second condition passes, we move to the third condition. If the third condition passes, then great. That means all three conditions passes. We know that our function is continuous. But if our second condition passes but third condition fails, we know that the function is not continuous and the category is a removable discontinuity. Okay. So we're going to keep referring to this as we go through our examples here. So let's look at first example here. Using continuity conditions, determine the reason why the following graphs are discontinuous. Then we categorize as removable or as non-removable. All right, now we can look at the graph and tell where the issue is, right? What is our C value here? Where's the point of discontinuity? When x equals what? 5. Okay, so that's our C value. We can obviously tell it's not continuous. We can maybe even tell what category that we're dealing with, but we're going to practice going through these conditions and spelling it out that way and justifying it that way. All right, so first condition. Our C value is 5, so we just replace our C with 5 and we make that read. Okay, so what's f of 5 equal to? 1. Okay, so that point exists. Now, if it doesn't exist, we keep going. Okay, so we never stop at the first condition. Think of the first condition as just gathering information. Okay, we're not going to make any conclusive determination. We're just going to keep going. Okay, so point exists. Great, we keep going. Okay, does the limit exist? It doesn't. Okay, but we're going to spell it out using justification from one side of the limit. So we already know the limit doesn't exist. So I'll say limit as x approaches 5. Don't forget, you got to write f of x here. You can't just say that the limit doesn't exist. We got to name that function that we're working with. And then to the side, we're going to justify it. We're going to say the reason why, because the one-sided limits are not in agreement, right? One's headed towards one y value, the other's headed towards different y values. So you're just going to copy this down exactly. The only thing you're going to replace is replacing that C with 5. That's all you're going to do. You're going to write it out exactly as you see it here. Okay, so there's a second condition, pass or fail. Fails. Do we keep going? No. We stop. We already know which category we're dealing with, so we can just go ahead and categorize it. So we know we have a non-removable discontinuity. Now make sure that when you write out the discontinuity, you got to specify the point, right? This is not discontinuous everywhere. It's just at a very specific point. So at where? At x equals 5. All this test is just for one single point, right? We're not testing any parts of the graph except for this one single point. Okay, I want you to try part B, and you're literally going to copy everything exactly as you see it. The only thing is just replace the C with the number that you're dealing with, okay? But you're not going to veer from this. Now, if I know what the value is, I'm going to write that value, but I'm not going to I'm going to copy this exactly as I see it. Okay, so refer to this, and I'm going to walk around and just kind of verify and confirm that you're writing down what I'm expecting. All right, so try part B. Oh, yeah.
Oh.
Part B. Most of, everyone's work looks good, so you're literally just copying everything that you have seen above. The only slight change you're making is replacing the C with 5, because you actually know what that C value is. But, you guys are, I saw most guys are doing well with identifying that function, that you're naming the function every time you put out a limit statement. And this is the type of justification that, the college board is looking for if there's a free response question dealing with, continuity. And we are also specifying exactly where that discontinuity is occurring. We don't want to just say removable discontinuity, because then that's assuming that it's everywhere, but it's only at a specific point. Questions? All right, let's look at part C. And go ahead and try this one, and I'll work through the same time that you guys do it. Okay, part C. Go through each of your conditions, and you want to write something for every condition. What's our conclusion? F of 3, what? Fine, or does not exist. Either way is fine. Does the limit exist? No. Okay, there's a subcategory, but technically that falls under does not exist, right? So we say limit. We can step into our one-sided limit. Say that they are not in agreement, even though, they're both showing positive infinity, that's not a real number, so that's why we can say that they're not. Do we need to go any further? If second condition fails, we stop. We can subcategorize it. Okay, questions there? So now we're going to explore continuity conditions without the graph in front of us and just relying on the expression. But we're still going to go through each of the steps exactly as we see it. We just don't now try to do it without the assistance of a graph, but instead of a function. All right, so let's look at part D. Part D says find the point of this continuity for the function. Is it removable? If so, what would we need to set the function equal to so that the value of the function is continuous? So the first thing is, what is our C value, right? We got to figure out, okay, we don't have the graph in front of us. So how are we going to know where that discontinuity is occurring? What do you guys think? Where can we look to find a potential issue in our function? Good. Focus on the denominator, okay? If there's a value that can cause the denominator to be 0, we know the function's undefined. If the function's undefined, whether it's a whole or asymptote, we know that's an issue for our function. So that's where we look for our C value. We look at the denominator. So our C value is what? 3. So let's go through our conditions and step through, right? Remember, the first condition is just information gathering. We kind of already know the function is not continuous because there's an issue at 3, but we're going to have to justify what which category. Okay, so first things first, f of 3. What happens when you plug 3 into the expression? 0 over 0. That is an undefined point. Right, so second condition, does the limit exist? So we're just going to write it out. Limit as x approaches 3 of f of x. Now f of x is this function. We're actually going to do some algebraic steps. So we're actually going to write the full expression instead of just f of x, because we're actually going to do some work with this. Okay, we want to find the limits. What's the first thing that we do? But before we factor, plug in that number, right? Plug in that number, and what do we get?
0 over 0.
0 over 0, right? So we know what type of category we're dealing with. We know there's a whole, right? We kind of see where this is headed towards. Okay? But so we know the limit exists. We're just going to go ahead and find that value. So what's next? Factor. Now we can factor, right? We have the green light to factor. Okay, what happens now? Cancel out, common factor. Reevaluate. We got 6. Okay, the limit exists. Okay, limit exists at 6. Now, look at the condition again. The condition has a one-sided limit portion to it as well. So I will say this, that you don't have to worry about the one-sided limit unless there's a piecewise function. If there's a piecewise function, that means you have two different functions on either side of our target. We're gonna have to rely on one-sided limit because you have two different functions. Here, there's only one function. We're doing with one function. There's no need to do one-sided limit because then you're just doing the same limit for all three problems. Or you're just doing this, you're doing three limits for the same problem, and there's no need to do that. So if only when you see a piecewise function, there's separate branches on either side of the target, then you gotta rely on one side of the limit. Otherwise, the full limit statement is just enough. It's a duplicate effort if we do one side of the limit. So do we look at a third condition? Yes, because second condition passes, right? We only stop with the second one if it fails, but we keep going because we haven't figured out exactly which category we're dealing with yet. So third condition, what do we do? Yeah. Check what you found from the first and second condition. Are they in agreement? They're not. Okay, so we're going to write out this statement and just simply say that these are not equal. Okay, the only thing you're going to replace is replace the C with what? What's the C value? 3. Yeah, that's it. You're going to copy exactly that third condition. Therefore, what type of discontinuity? Good. All right, so this is what we're after. So it's not a difficult concept. We just have to go through all these notations. One last thing here, guys, at x equals 3. Now, there's a hole in the graph, right? We know that if there's a hole in the graph, it's only one point away from being made continuous. So what can I do to make this function all of a sudden continuous? Where's the hole? 3, 6. So all we need to do is to define the point at 3, 6, right? Just fill in that hole. So it's asking, what's needed for us to fix that discontinuity? We just have to fill in that hole, order pair 3, 6, and all of a sudden, that hole will be filled in with functions. Okay, you guys have homework tonight. I sent out a text reminder to skip 7 through 19 because those problems we haven't gone to algebraically. So we'll push that. You can leave those blank, and we'll come back to it for Tuesday's homework. All right, go ahead and get your phones.
What are you over to? 33?
I didn't have to go like a real life.
How do you know it's 3?
Because
He was down in the.
you're always going to set the denominator.
I wasn't even yelling. Oh, okay.
Look for your discontinuity.
Don't think they shells.